Hello APC Mechanics students in Unit 6 Oscillations, Class 8, 6.1 Pendulum Motion Part 2. Now Section 1 Physical Pendulum, Simple Harmonic Motion. In the previous class we have seen the simple pendulum and we have mentioned the physical pendulum and the torsion pendulum. Now in today's video we're gonna discuss them. In the previous class we have seen the dynamics of a simple pendulum. The differential equation is given by d square theta by dt square plus g over L theta is equal to 0, and the angular frequency omega and the period are given by the following. And since the differential equation satisfies the form theta double dot plus omega square theta is equal to 0, then the type of motion is simple harmonic motion. And remember that we stated three assumptions. The most important one is assumption 3 is that the oscillations are very small. Today we'll see the extension of a simple pendulum known as the physical pendulum. A physical pendulum is a rigid body that can oscillate about an axis shifted from its center of mass. Some good examples of physical pendulum is this disc, in which the axis of rotation has been shifted from the center of mass, and the rigid rod, which can rotate around the left end or around its left end. So a disc that can rotate about an axis shifted from its center of mass, a freely rotating rod dropped from the horizontal position. For now, consider a disc of rotational inertia I around an axis delta shifted by distance d from its center of mass. Then I is the total rotational inertia of the disc around this pivot or the axis of rotation which is shifted from the center of mass. So here no need to apply the parallel axis theorem because we have applied it. However, if you have the moment of inertia around its center, you need to apply the parallel axis theorem in order to determine this one. D would be the distance of separation between the center of mass and the axis of rotation. The disk is of mass m and radius r. The aim of this section is to determine the differential equation, the angular frequency, and the period. We'll assume that assumption 3 still holds. Angles of oscillations are very small. However, we're not interested anymore in assumptions 1 and 2 because we're in the case of a physical pendulum. The strategy in solving this problem will be different and will build our results based on analogy. The length L of the pendulum will be promoted into a combination between physical quantities that hold the dimension unit of meters. The differential equation for a simple harmonic oscillator for a simple pendulum is given by theta double dot plus g over L theta equals to 0. Now g, it's fine, we can keep it as g, but our problem is just to replace L for a simple pendulum for something related to a physical pendulum. Now the physical pendulum is characterized by D, and it's characterized by I, and it's characterized by the mass m. Now if you think about it, so why we chose D and not R? Because D represents a physical significance, which is the distance from the center of mass to the axis of rotation. Now the three things that we have mentioned are M, D, and I, so we need to combine these together in order to replace L. L has a unit of meter, and you know that I, for example, for a disk is given by mr square. So if you need to convert this to have the dimension of length, simply divided by md. So L will simply be promoted to be given by I divided by md, which is also has the unit of length. Now you can notice that the fraction I over md holds the dimension of length. Then we apply the following promotion. L will be promoted to be given by I over md. Then our differential equation of theta for the physical pendulum becomes, instead of this, it will become that. And now we can do the arrangement, and the final version would be theta double dot plus mgd divided by I theta equals to 0. So here we didn't apply Newton's second law, we just derived the differential equation for a physical pendulum, knowing that assumption 3 still holds, and we know that it will perform simple harmonic motion. Then we just replace L by this fraction, and we get the following differential equation. It has the following form, which is theta double dot plus omega square theta is equal to 0, which means omega is given by the square root mgd divided by capital I, and the period would be given by 2 pi the square root I divided by mgd. Then that would be the angular frequency, and that would be the period. And here let me again specify that m is the mass of the rigid body, I is the moment of inertia about the axis of rotation itself and not the center of mass, d would be the distance of separation between the axis of rotation and the center of mass. Now what about the torsional pendulum? In this section we'll go over the torsional pendulum. Okay, here also let me mention that, so again we can write the following equation as theta double dot equals to minus mg capital D divided by I theta, which means acceleration is proportional to position, and this is a condition for simple harmonic motion. And again the pull of gravity would play the role of the restoring force. Torsional pendulum, in this section we'll go over the torsional pendulum. It's a rigid body that can rotate around a torsional wire. This is the torsional wire. The torsional wire is characterized by its torsional stiffness or torsional constant kappa. It is similar to a spring, but it doesn't drive an object left and right or up and down. It can drive an object to make it swing left and right, basically perform oscillations. A torsional wire, like a spring, is characterized by stiffness. It is characterized by a torsional stiffness or torsional constant instead of K, that would be kappa. The unit of kappa is in Newton's meter and not Newton per meter. The torsional wire provides a restoring torque or a restoring force that allows to drive the body into oscillations. If this is our equilibrium position and we shift or rotate the body with an angle theta 0, this body will start to rotate left or clockwise and anti-clockwise around this equilibrium line, performing oscillations and specifically simple harmonic motion. The restoring torque is given by torque is minus kappa multiplied by theta, which is basically an analogy with Hooke's law. Hooke's law is given by Fs is minus kx, so k is promoted to kappa, the position is promoted to theta angular position, where theta is the angle in radians from the equilibrium position, and suppose that our rotating body of mass m and radius r admits a rotational inertia I around the torsional wire. Then the differential equation of theta that governs the motion of the body is given by what? Simply theta double dot plus kappa over I. Theta is equal to 0. Why? Because remember, for a simple harmonic motion, for a spring, now here it's easier for us to do an analogy with a horizontal oscillator. It was given by x double dot plus k over m theta is equal to 0. Now k is promoted to kappa, m is promoted to I, and don't worry about the units because k is given by Newton's meter and not Newton per meter, so the unit of kappa is in Newton meter. Both the units of kappa and I would, so the unit of kappa and I, they agree in such a way that this equation agrees dimensionally. The angular frequency omega in this case at the period are given by what? This conforms the form given by theta double dot plus omega square theta is equal to 0, which means omega is given by square root k kappa over I, and the period would be given by 2 pi square root I over kappa. And now for the rest of the video we're gonna solve some exercises. Exercise 1, the period t of a pendulum of length L is measured to determine g at the surface of Earth. The equation used as period is 2 pi radical L over g. As we know, the mass of the pendulum of the bob is 10 kg and the length of the pendulum is 1 meter. So remember that this condition always holds true if the angle of oscillations are very small. Which of the following method would contribute to the expected error in the result? Now, a 10% uncertainty in the measurement of the mass. We know that the mass doesn't play any role. Approximating the value of pi is as 3.14. No, that's a good approximation. And sometimes we exceed this approximation by considering that pi square is 10. Variation in the value of g as the pendulum moves along its arc. Now G doesn't vary actually for oscillations. G varies whenever the height from the sea level is very big. So we can eliminate this using the average period of 10 timed oscillations instead of the period of 1 timed oscillation. That would increase the accuracy and doesn't increases the error. The only one that would cause an error is starting the pendulum swinging by releasing it from a horizontal position, yielding in a very big amplitudes of oscillation. So basically E would be the source of the error. To perform an experiment, students construct a pendulum by hanging a large solid metal sphere from a light string that is attached to the ceiling. A student pulls the sphere back to a small angle and release the sphere from rest. Small angle, it means that we are in the range of simple harmonic motion. Then the period is given by 2 pi square root L over G. And release the sphere from rest. The students measure the time it takes the sphere to swing back and forth 10 times and then divide this time by 10 to determine the period of the pendulum. This experiment is conducted for several different lengths L of the string, which of the following graphs best represent the date of the experiment. We know that if we're plotting t square, now t versus L or L square wouldn't give us a straight line. That would directly eliminate D and E. Now even L square doesn't work because that would be the period to the power 4. Then t square in this case would be 4 pi over G square multiplied by L, and the correct one would be t square versus L. Not only this, but the best fit line would be a straight line. Then C is the correct answer. A simple pendulum consisting of an iron ball suspended from a string is used in an experiment to verify the dependence of the period on the length of the string. The pendulum is pulled back about 5 degrees and releases small oscillations. We are in the regime of simple harmonic motion. The time for the pendulum to swing back and forth is measured. The procedure is then repeated for different lengths of the string. Which of the following is a modification that will improve the student's ability to test the dependence of the period on the length of the string, and explains why? Replacing the sphere and the string with a rigid bar, because a rigid bar better approximates as a simple pendulum. Now the problem with this statement is this one, because we know that whenever we're using rigid bodies, we're far from the simple pendulum, so we can eliminate A. B, replacing the string and the sphere with a rigid bar, because a rigid bar has more inertia. No, that's wrong. Giving the ball an initial velocity because the sphere will swing to a greater angle. That's wrong, because we need the angles to be very small. D, increasing the angle pendulum, the pendulum is pulled back because the larger angle better approximates a simple pendulum. No, that's wrong. According to assumption 3, the angles should be small. E would be correct. Why? Because measuring the time for the pendulum to swing back and forth 10 times and dividing by 10, that would increase indeed the measurement of the period. Okay. Now exercise 4. A small sphere of mass m is at the end of a light string of length L. The sphere is pulled back a small distance and released small distance, which means we are in the regime of simple harmonic motion. The sphere swings with a period of motion t. The process is repeated with a sphere of mass 2m. That's not important for us, because for pendulum the mass is not important, whereas the length of the spring is important. We have done a factor of change from L into 4. Now we can apply the factor of change. We can use the following because it's a simple harmonic motion. That would be 1 multiplied by 1, 4 divided by 1. We didn't change G. Radical 4 would be 2. And the correct answer would be B. And finally, exercise 5 as an exit ticket for today's video. A pendulum and spring both have 1 kg sphere attached to their ends and have the same length when in equilibrium as shown in the figure. They both oscillate with the same period. If the 1 kg spheres are replaced with 2 kg spheres and the amplitude of the oscillations are unchanged. Now here, okay, so the period is given by 2 pi square root m over k. And here the period is given by 2 pi square root L over G. If the mass changes, here the period would increase because we increase the mass. and here that wouldn't affect the period, so the period would remain constant. Which of the following is true about the resultant period of oscillation? So let's directly choose that the period remains the same. We can directly eliminate D and E. However, the period of the spring increases, making B to be the correct answer. Then that's it for me in this video, guys. See you soon and a new one.